Today we're going to look at a topic called Boolean algebra. Before we get into the depth of what Boolean algebra is, let's see what algebra means. Most of you would have heard the term in mathematics where we use the word algebra when we do not know the exact numbers in a calculation. We use letters instead to present the unknown values or the values that keep changing quite regularly. It's used in business when you want to predict sales, growth, and profit, and statistics, and almost everywhere in maths, except that we don't realize it that we are using algebra. Even though this is a very least favorite topic of most students in mathematics, it's still a very important topic to learn. Here's an example of a simple algebraic expression in mathematics before we jump into Boolean algebra. So let's say Casey, who's one of our Technocamps member, she's got X chocolates in her cupboard, right? And she likes chocolates, trust me. And Y orange juices. I don't know how much because I haven't actually checked her cupboards. And Alex, another member of Technocamps, he's got four fewer chocolates than Casey, but twice as many orange juice. They'll both like chocolates a lot. Now, how would you represent the number of snacks that Alex has? So, only if we know how much Casey has, we would know how much Alex has. But what Casey has is an unknown. We don't know. I haven't counted it. So, how can I represent what they both have? Or how what Casey has is going to impact what Alex has? So, let's represent the chocolates using the letter X. And let's represent orange juices with the letter Y. So that means Casey has got X plus Y snacks. So any point of time, if she's really hungry, she's got X plus Y snacks. It can be anything. Like today she's got 10 chocolates, but tomorrow she might have only 4 because she's eaten all 6 in one day. We shouldn't be eating so much, but well, if we are hungry and we have got a stash of 10 chocolates, why not? So if she's got X plus Y snacks, how much will Alex have? So Alex, we know, has 4 few chocolates. So x minus 4, because we know x is the number of chocolates that Casey has. So it will be x minus 4. Now, what about the orange juice? He's got twice the orange juice of Casey, right? So that will be 2 multiplied by y. So if she's got like 3 boxes of orange juices, then he will have 6. Well, Alex does make sure that he's got the this much amount as specified here always in a stash. So that would lead us to say that Alex has got x minus 4 plus 2 multiplied by y snacks. So anytime we know the value, like today she's got like 4 chocolates and 1 orange juice, I know for sure that Alex will have no chocolates because she's got only 4 and he will have 2 orange juices. So I can actually plan which one to rate, right? If I'm really hungry. And I have got permission to rate whenever I'm really hungry and I don't have any other option. This is called an algebraic expression. So we can substitute this value of x and y and actually find out what the stash is. So this is a very simple example. So in algebraic expressions are used for any of these kind of examples. So for example, number of socks you have or the age between the siblings or cousins. I mean, you will find a lot of questions that come out like that. So how is this different from the term Boolean algebra? It's uh, it's it's in a way similar, but slightly different too. So this was introduced by a fellow called George Boole in 1847 when he first wrote his a book about it, and it all actually comes from the logic, mathematical logic part. So it uses variables like we use in algebra, like x and y, but only that it doesn't use the values x and y as is. It uses truth tables to evaluate it. You don't have um, just a simple expression, you have truth tables to verify it. And also, the key part of this is that whereas x and y in algebraic expression can take any number value, like any value from, I don't know, 0 to whatever the limit is for numbers, in Boolean algebra, you can have only 2 values. Like, for example, chocolate can have only 0 or 1. That means there is a chocolate or there isn't. So there's only two ways of representing it. You cannot say there is 10 chocolates. You can say there is a chocolate or there isn't a chocolate. Okay? So it's always going to be true or false. And you can represent the true or false using 1 for true and 0 for false. So it's easy. So you don't have to write true everywhere. You can just say 1. So if I say 1, that is equal to true. That means it looks like a true or 1. And 0 is false. Okay. So we're going to see three basic operations of Boolean algebra. So Boolean algebra has a lot of operations that you could do. So what we're going to look at is three basic ones and then take it further from there. How are you going to represent them? Like, okay, we have got expressions in algebra. You will have expressions here too, but that's not part of this video. That's only for like once you understand the basics, and then you can play around with like additional expressions. But for now, we are going to use a Venn diagram and truth table. How does a Venn diagram and truth table look like? So a Venn diagram is usually used in set theory. If you have done set theory in mathematics, you will have done Venn diagrams for that. So we're going to use something like that. So um, for people who haven't done set theory or Venn diagrams, it's just a circle representing a item. For example, if I represent chocolate and orange juice, so the purple one, the purple circle represents chocolate and the green circle represents orange juice. So I can have, so why have I intersected it? We'll talk about it in the next slides. But if you want to remember how the Venn diagrams usually look like, take two rings out of the Olympic symbol, right? And represent it. It doesn't have to be in a particular color. The color is only for you to understand the concepts here. And the table is exactly what it says. It's a truth table, so that means you'll have the values true or false in them. Let's go with the first operation. It's an OR operation. So even before we go to the OR operation, let's make ourselves a cup of drink, right? I have got only two options here, one either coffee or milk. Now, I don't know how you take your coffee, but I like my coffee with milk. And if you like one of my friends in Technocamps, Luke too, we call him, he likes his coffee without milk. So he likes plain black coffee. He shudders at the thought of having a coffee with milk. And there is one more person, again, a Luke Clement. He doesn't like coffee at all. So he drinks milk only. So we have various choices. So when there is only two options given to you, you still have options or choices to make. So I can have just plain coffee, black coffee, and you can have plain milk if you're fancy, like if you fancy, and it is usually good to drink, except that I'm too old to not be bothered with that, to be honest. And well, you can have, like me, coffee with milk. So this Venn diagram represents that Luke 2, for example, has or likes only plain coffee. He doesn't have a shred of milk in it. So I have colored only the portion of coffee where the milk doesn't touch it. Okay, so that means it's plain coffee only. And this is Luke 1 or Luke Clement, who likes only milk. So he doesn't touch coffee at all. He doesn't like coffee or tea. So he doesn't touch any part of coffee and he has only the milk. And this is me. I mix both coffee and milk, and that's my guilty pleasure, right? I love my coffee with milk and probably a good spoonful of sugar. And there are a couple of them who doesn't drink either. They like their orange juices, they like their teas. So Lauren, for example, likes a peppermint tea. So she doesn't like coffee or milk, so she doesn't touch either of them. So we've got four options here, just with two inputs. So I've given you two options. I've given you coffee and milk, but you can create four different options out of it, right? Now, how is this related to OR operation, or like how is this related to Boolean at all? Now, let's say a coffee machine, right? In this coffee machine, you have got two buttons, say coffee and milk. Well, you have more in real life, but let's assume that you have got only two buttons. Now, I've got C, which is coffee, and M for milk. I've got these four options as described earlier. So, and What will happen if Luke 2 goes and presses C? Will the coffee machine deliver him something or will it give him coffee at all? Yes, it will give him coffee because he's asked for plain coffee. So that's fine. What about Luke Clement? If he goes and presses M, will it give him milk? Yes, it will give him milk because why not? We can still have plain milk. Now, if I go and press coffee and milk together, will it give me coffee with milk? Yes, probably it will because why not? It has to just add coffee first and then probably a slightly thicker in espresso fashion and then add milk on top. It's perfectly possible for it to provide me. And for example, Lauren goes there and she sees that there is no tea option there or hot water for her. So will the machine? So she's not going to press anything. Is the machine going to give her something? No, it shouldn't because you have not pressed anything. If the machine is going to spurt some milk or coffee, if no one has pressed any of those buttons, then we have to get the machine repaired or fixed. Okay, so so we know that we've got these four options now, right? Just with two inputs, I've got coffee and milk, we have got four options. Now let's convert that into a truth table. So I've got coffee and milk. So whenever I've just got coffee alone, I say true. So in the first case, Luke 2 wants just coffee. So he says true, or he presses coffee. So the value is true or 1. And he doesn't press milk, so the value is 0. And the machine will give him coffee. So the dispense action is set to true. Similarly, for the second one, Luke Clement goes and presses only milk, so coffee is set to false, milk is set to true, and it will give him milk. So the dispense action is set to true. For me, I go and press both. So it's going to be coffee true, milk true, dispense action is true because it's going to give me coffee with milk. And Lauren goes there and she doesn't press anything. She sees that there is no tea option and she comes back. So that means both of these buttons are not pressed and so it is not gonna dispense anything at all. So we say false. So based on your action, whether it is done or not done, or is it there or not there, you say true or false. And also what will be the result of that? Is your action having any result at the end? So we say true or false or 1 or 0 accordingly. Now, the key part for this particular truth table or the diagram that we have seen is look at where the truths is. So the dispense action is a final action. So where do we have the truths there? We have got true here, and true here. That's well and good. So why did the machine dispense the action and what condition did it dispense the coffee or milk or coffee with milk? It, it dispensed something when either coffee or milk or both were pressed. So all you needed to press was either coffee or milk or both. So in case where you did not press anything at all, it didn't do anything, so the result was always false. So this is an example of a OR operation or Boolean operation. I have replaced the true and false with ones and zeros here, so it's easy for you. Can you see all the ones on the output? So some output will be done if either of the input or both the inputs are 1. So what does it mean? For OR operation, you need two input. You need two values in the first place. You can't just have one option called coffee and expect an OR operation. That's not going to work. Okay? So for OR operation, you need a choice. You need to have at least two choices, a minimum of two choices. And now either of them should be set to true or 1, or both has to be set to true or 1 for the final output to be 1. So this is the truth table for the OR operation. Now let's go to the second one, AND. I'm not sure how many of you have visited banks when you go and place something in your safety deposit boxes. There are various ways the bank operates for the safety deposit boxes in various countries. In India, where I have one, we used to have like the bank used to have a master key, which they can't open my box, but they have to open one of the locks in the box, and I should have a key where I use it for the second lock. Only if both the keys are in place will the box open. Whereas here in Halifax and Lloyds and other banks, what you have is a room for which you need an access card. So you have to, you can search for safety deposit boxes in Halifax or Lloyds, and it will give you a video of how it looks like. So ideally, you will have an access card with which you go to the room where your safety deposit box is, and then you either have to have a physical key or your touch your fingerprint to actually open the box. So let's use those two cases here. You have an access card to go into a room where your safety deposit box is, and you have a key to open your specific, because in a room you could have 10 or 15 safety deposit boxes belonging to different people, and only people who have access to that room can go and operate their safety deposit boxes. So given that we have two of these inputs, let's see again what are the options you have. I can have just the card, but not the key. That means I can enter the room, but can I actually open a safety deposit box? I can't. So, and then I can just have the key. I forgot my card, so I don't have access to the card, but I snuck the key from someone. What will it do me? Will it do me any good? Then I have both the card and the key, and I don't have either. So just look at the third one here. We are not combining both together, right? We are not having them all together. I need someone who's got both. Now, for something like this, we've got these four options. Now, what does the first one mean? With just my card, can I open a locker? No, because you need the key to actually open this particular specific box. I can go into the room using the card, but what about the box? I need the key. What if I just have the key? Well, you can't even go into the room in the first place, so how are you going to access your locker? You still can't open the locker. What if I have both? Yes, it will allow me to access the room and then go and open my locker. And what if I have neither? That means obviously you shouldn't be allowed inside the bank at all to even try. So because you don't have the card or the key. So let's convert this into a truth table. If you see here again, if I just have the card, I say true. If I just have the key, I say true here. So the rest will be false. If I'm not able to open the locker, I'll say false because, well, I can't. So the action will be false. So let's see what happens in this case. There's only one output where it has a true set. That means action, the open locker is activated only on one condition. And what condition is that? When both my access card and the key is set to true. So irrespective of whether you have just an access card or the key, it wouldn't work. In this case, you have to have both of them together. So this is different from the OR operation that we saw. Why? Because if you allow that to happen, just like an OR operation, that is a mistake because the system will fail. Anyone and everyone can be allowed to open it, so which is wrong. So for this system, we have to ensure that you're opening the locker only if the access card and the key are set to true. So this is how the truth table looks like. I have replaced all the truths with ones. So if you see here, there's only one for output. And that is because both the inputs are set to 1. So the difference between the and the OR operation is in AND operation, you still need 2 inputs for sure. You need a minimum of 2 inputs. And the output will be true or will be set to 1 if and only if both inputs are true. Okay, no other scenario it will allow you to actually do the operation unless all the inputs are set to true. The third one is a very easy one, which is called a NOT operation. So NOT is a special operation where you have only one input. So it's exact opposite of the input. So output will be always opposite of input. If I ask you to do something and if you don't do it, that's a not operation, and we are so used to it, right? We always like to not do what our parents tell us to do. My nieces do that all the time. The moment you tell them don't do something, the first thing they do is that exact thing that we ask them not to do. So here is an example. So if I have a all workers set or a group of all workers, and in the center I have got essential workers, if I say not essential, so that means the green shaded ones will be the not of the essential workers. So for now, not of the essential workers should stay at home and have fun. Okay, so the truth table will look like true, input will be true, output will be false. If you have false as input, then the true will be output. It just inverts it. It just does the exact opposite of what you've asked it to do. So you need only one input for that. Okay, so this is the basic Boolean operation. You have OR, where you combine both, because either of those should be set to true. If either of them or both of them are set to true, the output will be true. In AND, both of them have to be present for the result to be true, and not of something is exactly the opposite of what you're asking to do. Okay, now this is all well and good, but why are we learning this? You are using this every day when you're searching for something on YouTube or Google. You don't realize it, but what you can, now that you know what they are, you can use it to do an effective search and safe search too. So I'll demonstrate in the second video how to do those things. And the second one is using logic circuits in computer. What do you mean? So if you open up a computer, you can see a lot of small circuits that will be there. So all that you do, all the games that you play, they're all converted into actual actions using those circuits, and all those circuits are built using these operations. Okay, so we have various applications of the Boolean algebra. So we'll look at them during the next video.